So welcome. Thank you for joining me today. My name is Scott Kidder. I'm a principal software engineer at Mux here in San Francisco, actually just a block from where we are today. So today I'll be sharing with you our video access log processing system that we've built using Apache Flink. So here's the agenda for the talk. I'll begin with a quick background on Mux, just for context. Then I'll follow it up with a web video primer, explaining how most web video is delivered. Then we'll cover some of the challenges with using a utility billing model for billing based on video usage. And then we'll cover the details of the log processing system that we've built at Mux. And if we have time, I'd love to take any questions that you might have. So background on Mux, in 2016, we launched a Mux Data product, which is an analytics service for video. It provides insights into quality of experience issues for video playback on websites or mobile apps. So Mux Data is very easily integrated into any video delivery application, exposes metrics like buffering, playback errors, and more. So our experiences building Mux Data and operating it have led us to see that it's still very difficult to deliver internet video well and provide a good experience. So earlier this year, we launched Mux Video, which makes publishing internet video as simple as making a REST API call. You just provide us a URL for your source video, and we'll automatically select the optimal video encoding settings and package it for delivery. And we also provide no commitment utility billing, which means you only pay for the video that you store and the amount of video that you've actually delivered, which is the subject of this talk. It requires processing the access logs to actually make that possible. So web video primer. So how does web video even work? What is happening in the background when you visit Twitch, Netflix, or YouTube and start playing back video? What sort of requests are being made by your browser, smart TV, or your mobile app? So playback is always initiated by the video player. Most adaptive web video is delivered using a protocol called HTTP Live Streaming, or HLS, which was developed by Apple and initially released in 2009. So HLS relies on M3U8 manifests, which were originally designed as just generic playlists, but they've been extended to support video streaming as well. So the sequence begins with your video player making a request for the master manifest. The master manifest describes all the different renditions that are available for the video that you intend to play. Each rendition might have a different video resolution, bitrate, language, or some other distinguishing feature. The player then selects the optimal rendition for your current playback circumstances. Next, the player requests the selected rendition manifest, which again is a M3U8 playlist, which includes a sequence of URLs for video chunks, as well as their timing information to facilitate seeking within the video. Lastly, the video player begins requesting video chunks so that they can be decoded and played back. If the player decides to change renditions, perhaps because the network bandwidth is increased or decreased, then it will request a different rendition manifest and resume playing a different set of video chunks. So which systems are involved in this chain of requests? So you begin with the playback device on the far left, which makes a request for the manifests and the video chunks through the content delivery network, or the CDN. And in the event of a CDN cache miss, it'll then forward the request back to the video origin. So Mux performs just-in-time transcoding of video, which means that in the case of a cache miss, we'll actually read the high-quality video mezzanine chunks from storage at request time, transcode them, and stream the transcoded bytes out through the content delivery network using HTTP chunk transfer encoding back to the client and cache them at the CDN to service future requests. So this is very different from how most video services worked in the past. They typically transcode all the renditions up front, which is expensive both in terms of compute and storage, especially for user-generated content that might not ever be played. So in this case, we're only transcoding and storing renditions for content that is actually accessed. So as I mentioned earlier, utility billing requires us to know exactly how much video is served, and we do that by processing the CDN access logs. So what are some of the challenges of doing utility billing? So it basically just means paying for what you use. Just like the electricity usage that you pay for at home, it's metered. The bulk of your bill is based on what you use. If you use more, you pay more. If you use less, you pay less. So applying this model to video is very appealing to people who are working maybe on a new project where they don't necessarily know up front what sort of volume they're going to be dealing with, and therefore don't want to commit to an expensive pricing plan up front. So in order to build based on video usage, we need to enrich each video access log record with details about the corresponding video. We do this by querying our asset index database. We need information about the video chunk that was requested and attributes of the video rendition, like the resolution, bitrate, frame rate, etc. We also need to be able to avoid falling victim to a thundering herd type scenario. So CDNs do an excellent job of shielding our origin from requests for manifests and chunks in the case of viral content. However, the CDNs will also provide us with a log record for every single request that was made, whether it was absorbed by the CDN or came back to our origin. So as our CDN log processing is processing these huge spikes in logs, we need to make sure that it doesn't negatively impact other internal services back at our origin during the enrichment process. Additionally, the logs that we receive from the CDNs are not ordered. This is mostly an artifact of how the CDNs aggregate their own logs from their many points of presence around the world before making those logs available to us. There could also be several hours of delay from the time when a manifest or chunk request is made and when it eventually is delivered to us. So we calculate hourly usage details by adding the duration of video that was served for a chunk to an hourly window, which I'll cover later. So these windows are scoped by customer account as well as by video asset. So we can say for a given hour exactly how much video was served for a customer or for a specific video. So let's look at the log processing system that we built at Mux. So the first step is initiated by the act of watching video. So video player makes a request, goes to the CDN, may or may not go back to the origin depending on if that content is cached. With step 2, we actually get down to the details of handling logs. So we've got, in this diagram you can maybe see in the upper right there, we've got log collectors, which sit behind a load balancer that permits inbound connections on HTTPS and syslog. So many of our CDN partners will stream logs to us as they're generated. Additional CDN partners that we're currently trying to integrate with right now have APIs that we can pull for CDN logs. Either way, those two mechanisms of getting access logs result in logs being written to a Kafka raw logs topic. So our CDN log collectors are written in Go. Most of the services that we run at Mux are written in Go. The log enrichment app is really kind of the exception to the rule. So our collectors run as Docker containers in Kubernetes cluster. The collectors themselves require very little CPU or memory resources, so we can scale them horizontally very easily and cost effectively. And they've got a simple task, which is to parse the CDN log messages from either comma separated value format or JSON, whatever format is used by the CDN, into a protobuf-based message format that we use for representing all CDN access logs. So the serialized protobuf messages are then written to a Kafka topic for raw log records. So Kafka is probably something that you guys are all familiar with. It's just a high-performance distributed log that's really ideal for storing access logs like this. And as usage increases, we can scale the number of Kafka brokers or the number of partitions associated with the raw logs topic to deal with increased write throughput requirements. So next we'll introduce one of my favorite parts of the architecture and is what's actually referenced by this talk, which is the log enrichment app. So from the Kafka raw logs topic, those records feed into a Flink log enrichment app. So we need to enrich the log records with details about the video asset. And this can all be done asynchronously. That's why the collectors are simple stateless services that get the log records, quickly write them to Kafka, and then we can asynchronously enrich them. So the Apache Flink is a platform for building stream processing applications in Java or Scala. So this log enrichment app reads from the raw logs topic, performs log enrichment, and then writes the enriched logs to a second Kafka topic that has a much longer retention period. So the raw logs topic, we only retain those records for 7 days, but our enriched logs we keep for much, much longer, on the order of many months, to support debugging operations, auditing, as well as data mining. So the log enrichment Flink application has its state distributed across a variable number of Flink task managers. And Flink makes it very easy to scale the amount of resources that you want to devote to a job simply by changing the degree of parallelism specified when you're submitting a job. So I actually had to do this just this morning, which I'll come to again later in the talk. So enrichment consists of adding asset details, network details, geographic information about the client that made each manifest or chunk request. So asset details that are particularly relevant to billing include the source video duration and the rendition settings. So the rendition settings also include the chunk target duration. So HTTP live streaming requires that each video chunk have a target duration, which varies depending on the use case. So live video generally has a smaller target duration. In our case, it's about 2 seconds. On-demand content has a larger target duration, which is like 4 seconds. And that's because you have different latency requirements. And so knowing the target duration helps inform the calculation of how many seconds of video were served for a particular chunk request. So we also identify the network ASN, or autonomous system number, of the internet router that sat between the client and the CDN. This is important because it helps us identify slow or poorly performing internet routers and potentially perform dynamic CDN selection. So we support multiple CDNs, and identifying CDNs that are performing better or worse in different geographies helps us, at the time of rendition manifest request, select the optimal CDN. As we're rendering that rendition manifest that has all those chunk URLs, we could choose to deliver those chunks through one CDN or another. And those can have performance cost differences. So our asset details are kept in a CockroachDB cluster that spans multiple data centers. And the asset information about the video is mostly immutable. The only thing that really changes over the life of an asset after it becomes ready is it transitioning from ready to deleted. The video details generally don't change much. And we want to avoid overwhelming our CockroachDB cluster with reads for data that doesn't change much. So our Flink app, when it's performing log enrichment, will first query a Redis in-memory cache for asset details, and only in the event of a Redis cache miss will it query our asset index, which will then proxy that request to CockroachDB. Transaction support in Flink and Kafka is also an important feature that we take advantage of. So Flink log enrichment app will periodically checkpoint its state to HDFS. So we do that every 5 minutes. And if the Flink app is restarted unexpectedly, maybe one of the task managers crashes or one of the external services that we need to interact with returns some sort of error code that we cannot recover from, the Flink app will then be resubmitted or restarted automatically, and it will resume from that earlier checkpoint, which results in us reading messages from an earlier position in the Kafka raw logs topic. This leads to reprocessing of messages and messages being written again to the enriched logs Kafka topic, but this time as part of a separate transaction. So the transaction that was in progress when the Flink app crashed will never be committed, and therefore downstream consumers on that enriched logs topic will ignore those messages. So downstream consumers only process committed Kafka messages. This is important because we don't want to process enriched log records multiple times, aka like double billing or double charging. So we have those exactly once processing guarantees, courtesy of Flink and Kafka, which is very cool. And we also have the log enrichment app write performance metrics minute by minute to an InfluxDB database that drives many of our Grafana dashboards for internal monitoring. So the chart that's shown here is something that I added just this morning because we had a new customer that launched. It's a self-sign-up service, and so we can literally get bombarded with huge volumes of incoming video being ingested as well as video being delivered without any warning. So this huge spike in volume led to a huge influx of CDN access logs, and we had to scale the number of Flink task managers to process these logs in order to keep up, but it didn't result in any change in the calculations made for the purpose of billing made by the Flink. It simply ran slower, which is the desired behavior. So lastly, utility billing usage calculations. So we've got a second Flink app that reads these enriched log records from the enriched logs Kafka topic. It uses event time processing to assign a log record to a 1 hour window that covers the time of the request when it was made. So we support up to 3 hours of allowed lateness. This means that we don't consider a 1 hour window either for calculations across a customer environment or for a specific video asset. We don't consider a 1 hour window to be final until we've received a log record that is at least 3 hours later than the most recent edge of the window. So this is essential to processing out of order and late CDN log messages. And so Flink's support for watermarks and allowed lateness really is what makes this pretty easy to achieve. And so once a 1 hour window has been finalized, we'll pass it on to our Postgres billing database. So we maintain the total number of seconds of video served for each customer and for each video asset in a given hour. And calculating billing totals or billing reports for our customers is as simple as summing up the number of seconds of video served for a customer environment over the given time range. So in summary, billing on video usage requires processing large volumes of logs. Apache Flink and Kafka have made a great foundation for building scalable stream processing applications, and their support for event time processing, transactions, and allowed lateness have been critical to the work that we've done. So thank you again for your time, and I'd love to answer any questions that you might have. Yes?
How did you determine the window for allowed lateness? Like you said that it was like
Yeah.
3 hours, so I was wondering how you
Yeah, so your question was, how did we determine the right amount of time for allowed lateness, 3 hours? So that's based on the current CDNs that we integrate with. So they have a guarantee that they'll provide us logs within 3 hours. So as we begin to integrate with more CDNs and maybe they don't provide as timely logs, we'll have to expand that. And the implication there is that we won't be able to finalize those windows until much later. Yeah, thank you.
So following that same theme, like you mentioned, your video kind of data, your log data is very bursty. If you have suddenly a viral video, a million people could view it. So essentially you have to keep a 3 hour window or less depending on what you want to do on your processing versus event time, which means you either have to do a bunch of manual scaling if you guys start to become very popular, or there has to be some sort of auto-scaling. Are people auto-scaling Flink right now?
Actually, because we're using event time processing, it can take longer. It can take longer than 3 hours. We're not using processing time. The time is an artifact of Flink, event time versus processing time. So the processing within the Flink application can take much longer than 3 hours and still provide deterministic results.
So are you keeping like an in-memory cache for longer than 3 hours?
Yeah, so Flink will maintain an accumulator that a windowed accumulator that is good for a period until we see a message that is more than that allowed lateness in the future.
Okay.
So it's not relative to the current wall clock time. It's relative to the time on messages that are flowing through the Flink app. Yeah.
And the auto-scaling question?
Yeah. So we don't support auto-scaling at this time. So if we determine that we need more CPU or memory resources, then we'll do an atomic cancel with save point on the Flink app, which writes out the state to HDFS and then resubmit it with a different parallelism value, maybe having it run on more or less task managers. And Flink will then automatically redistribute the state across the new task managers.
Is that what you had to do this morning?
That's exactly right, yeah. So we went from a certain number of task managers we added more task managers and just had it run across a larger cluster. Yes?
You mentioned that you have Redis in front of CockroachDB for caching.
Yes.
Is there a benefit to do it in Redis as opposed to keep the cache in Flink?
That's a good question. So you could end up having storing state within the Flink application is kind of discouraged because Flink manages its own objects in memory. And if you're then starting to kind of pollute that a little bit with your own cache, then it could conflict with Flink's own memory management, as I understand it. And it's running a separate Redis cache is cheap and easy. So, yes?
How do you deal with failures of log collectors? So the very first step,
Yes.
collecting the log and the thing dies. What do you do?
What do we do with the scaling of the log collectors?
How do you know that they are up and alive and giving you logs? What if one of them shut down?
Yeah, so that's a good question. So we've got a service called RunScope that periodically tries to play video through our system. And it provides a complete loop as far as like ingesting video, playing video. So we expect to see access logs for those video views. So if we don't receive those video views coming through the log collectors and into the Flink app, then we'll page. Yeah, and then I'll get woken up, which I don't want to get woken up. Yes?
Do you guarantee or do any work to guarantee lack of duplicates from the CDN logs?
Yeah, so with our CDNs, we require them to uniquely tag each CDN access log record with a UUID. So we'll try to do deduping using the UUID that's provided in the CDN access log record. Yeah.
All right, let's
Yeah.
thank Scott again for a great talk.
Thank you.